So let's talk about Bloom filters. Bloom filters are approximate data structures, also called as probabilistic data structures. We'll understand it in depth, don't worry. What it does is, it says with 100% certainty that an element does not belong to a set. What does this mean? This means that, for example, let's say Instagram wants to recommend reels to you. But does it make sense for Instagram to recommend the same reel that you already watched before? Because then you are literally seeing that exact same reel that you saw some time back. So which means that whenever you are recommending something to your user, you typically have to ensure that you are showing them something new, something exciting, not something that they've already watched before. Which means that for you to do this, you have to recommend something to the user that they have definitely not watched. Correct? A way to implement. Now, how would you implement? Let's say you didn't know about Bloom filters. How would you implement? The first thing that comes to your mind is, hey, let me store everything in set. For every user, I'll keep track of everything that the user that the user ever watched, the IDs of the post, and I would store them in a set. That's the first thing that would come to your mind, and which is perfectly fine, because now what you can do is you can have a user. For every user, you are maintaining a set of everything that the user always watched. Whenever your recommendation engine is recommending something to your user, it would check this set. If the key is not present, it would recommend it. If key is present, then it would discard it. This solves the problem. But people watched hundreds and thousands of reels every day. Over time, the set would grow to be very huge, which means that for you to check the existence of a particular key, you have to check the set. But you say, Arpit, what's the problem? I'll store the set on the disk. Think about it. If you store the set on the disk, how will you check it? For you to check it, you have to load the entire set in memory, because sets are what? Sets can be implemented as a binary search tree. Right? Which means that you would have to load the entire set in memory and then check for existence. Which means that when even millions of users watch hundreds and thousands of reels every day, over months, the amount of data that you are collecting is huge, and you cannot have this much of memory to store this information. So this is super expensive. This is also time consuming. So can we do better? This gave the rise to an approximate data structure called Bloom filter. Or this problem gave rise to Bloom filter. A key insight that helps us understand where Bloom filters shine. The key insight is, when someone has watched something, you cannot take it back. For example, in a set, when you add something, you can also take it out. Set offers you that operation to add and remove. But if you think about it, when someone has watched a reel, do they unwatch it? No, it's registered. The view is registered, which means that you are relaxing. You can relax the constraint that you can take out from the set. Right now, because now you don't want to take something out from the set, so can you do something with it? So almost all variants of data structures start from something very similar, where it's okay, where they relax some constraints and they make something better. So here we relax the constraint of, okay, it's fine if we don't have an ability to take something out from the set, but we need better space efficiency or better time efficiency, right? So you get some, you lose some, which is perfect. And the entire domain of computer science is filled with trade-offs. Always remember that, right? Okay. So once a post/reel is watched by you, we do not take it out of the set, which means that, hey, do I really need to store the actual post ID? Because I'm not going to take it out. This forms the crux of Bloom filter. So whenever you hear the term filter implies a bit array. A normal simple bit array, not even byte array, bit array of bits is called as a filter, right? So Bloom filter is a filter created by a researcher named Bloom. That's why it's called as Bloom filter. And the idea is, here we take a very simple example to understand what's happening and how it works, right? We'll then take a look into how to use it, how it scales, the disadvantages of it and whatnot. But let's understand how it works. So in case of Bloom filter, let's say I take a bit array of 8 bits, which is 1 byte. right? Now let's say I want to store words in it. So if let's say I want to store apple, given that when we put something, we are never going to take it out. So it is fine if I don't store the actual string apple in it. So what I do is I take apple, pass it through the hash function, mod 8, because I have 8 bits, I get, let's say, output 2. This hash function can be MD5, SHA, any hash function, murmur hash, pick your favorite hash function. But the idea is you get a number in mod 8. Because here there are 8 bits. You may have larger Bloom filter of, let's say, 10 KB. So this would be 10 KB. And like 10 into 8 into 1024. Right? Those many. So whatever the length of the bit array is, by that you mod it over here. This way what you get is you get an index that needs to be set as 1. So for this apple I get 2. So I set the second bit as 1. Then let's say I have another word called ball. When I pass ball through the same hash function mod 8, I get 6. So I mark the 6th bit as 1. Then let's say the third word I get is cat. Cat, pass to the hash function mod 8, I get 2. I mark the second bit as 1. Remember, the second bit was marked as 1 by apple also. Now it is done by cat also. Right? Now, let's say this is what I stored. I only stored existence of 3 words, apple, ball and cat. Right? Okay, let's take a look at the space. If I were to store the actual words apple and ball and cat, apple is 5 bytes, ball is 4 bytes, 9 bytes, 10, 11, 12 bytes here itself, right? But what we are doing is we are just storing it in 1 byte, 8 bits, right? So you see a humongous space save, right? This is the space advantage that you get by using Bloom filter, right? Now here I took a very simplistic example of 8 bits. But now let's see what if I stored these 3 words. Now let's say I want to check, does dog exist? We only added 3 words, apple, ball and cat, right? Now I want to check, does dog exist? So I'll pass the dog through the exact same hash function, mod 8. Let's say I got 5. I'll check what is the 5th bit. 5th bit is 0. Dog does not exist. And indeed, dog does not exist. So my Bloom filter says no, it means dog, and Bloom filter says no because the bit is set to 0, which means my dog definitely does not exist. Correct, right? Now let's say I check for elephant. When I pass elephant through the hash function mod 8, let's say I get 6. So I check 6. 6 bit is 1. But I just stored apple, ball and cat. I didn't store elephant at all. But when my Bloom filter says yes, it means that elephant may be present. It is not saying it is present. It says it may be present, right? This is the idea of Bloom filter. So when Bloom filter says no, it says with 100% certainty that the word is definitely not present. But when my Bloom filter says yes, it means that my word can be present. I have to check it explicitly in case you'd want to do anything with it, right? In most cases, you typically discard. You don't want. You'd want, like, for example, when Instagram is recommending you reels, it will not recommend you at all. It would not have to check, oh, did I actually send this, like, did I actually recommend this or not? It does not. It just discards it. But what it would definitely do is it would definitely show you something that is definitely you something have never watched. That is how recommendation engine works. So you typically don't care of this use case. It's okay to miss out on some data, but what you would want to focus on is when you are serving something to the user, you definitely want to serve something new, which is where Bloom filters shine, right? So you are picking up Bloom filter for this use case where it says no, you definitely know that it is not there. Highly optimized way for you to get that information and use it. Right? Okay. You have clearly seen how Bloom filter is very space efficient. We store existence of 3 words, apple, ball and cat within 8 bits. And we could store even further more, right? But here you see the benefit of it, that Bloom filters are really space efficient. So you don't need to store massive sets holding massive information. So which is why people adopt Bloom filters at scale, because at scale, it's okay to have some false positive rate. This is called false positive rate because the word elephant was not present, but Bloom filter said it is present, is false positive. It is falsely classifying it as existing, but in reality, it is not false positive, right? So here's we get space efficiency, we get time efficiency, but we get false positivity. You get some, you lose some. What you are losing on? You're losing on correctness. So when Bloom filter says no, it is 100% correct. When Bloom filter says yes, it might be incorrect. Right? Okay. Now I uttered the word false positive. Now you can clearly see over here that as I increase more and more words that I insert in Bloom filter, the more and more bits will be filled, and eventually a time would come where all the bits will be 1. And what would happen? No matter which word you give, your Bloom filter will always say yes present, which is wrong. Right? So over time, as you keep on adding more and more words to your Bloom filter, the false positivity rate increases. This is a problem with Bloom filter. So always ensure that your Bloom filter, because when you create a Bloom filter, it's not that Bloom filter is infinitely growable. When you create a Bloom filter, you specify the size of the Bloom filter. That hey, this is how big I want my Bloom filter to be. Let's say 1 KB. 1 KB means 1024 bytes, which means 1024 into 8196 bits. That is the size of the Bloom filter that you are operating with. And I'm taking 1 KB as an example. You can start with any value that you would like. Right? So now, as in when you keep on adding more keys in that, earlier the false positivity rate will be very less. But then over time it would grow, because now as more and more bits starts to fill out, for more and more keys that you are checking, it would say yes, it is present, but in reality it is not. So what you have to do is you have to tune the size of the Bloom filter depending on the number of keys that you are putting in. There is a formula, there is a very standard formula to do that. You are just a Google search away to figure out the size of the Bloom filter for a false positivity rate that you are interested in. Right? So if you want lower false positivity rate for a certain number of keys, you want to have a big enough Bloom filter. But how big? That formula will tell you. It's a very simple formula, but I want you to explore that. Right? Okay. So what happens when, let's say, you started with 1 KB of Bloom filter, you inserted a lot of keys, let's say 1,000,000 keys in that. Now your false positivity rate is very bad. Right? Now what you want to do is you want to make it better. Now how will you make it better? You cannot take anything out from the Bloom filter. You cannot grow it, because as soon as you grow the Bloom filter, your mod function, your hash function changes, because here you had 8 bits. That's why you did mod 8. You just cannot extend it. This would become 16, then the mapping would change. That's the limitation of hash based stuff, right? So you cannot do that. So what would you do is you typically try to minimize that in the first place, but you will have to recreate the Bloom filter with a larger size and populate it with the keys again. So literally all the keys that you put in the Bloom filter, you would have to iterate through all of them. Maybe you would have another database where you are storing it, because this cannot be your source of truth, where all the pictures or all the reels that you saw cannot be your source of truth. It will be present in some database. This is just an auxiliary data structure helping you get the performance out of your system. This is not the source of truth. So what happens is you go through the source of truth, iterate through all the keys and re-ingest it in this enlarged Bloom filter. It's a complicated process. It's a lengthy process. So you typically over provision a Bloom filter. You know how amount of data you would store in. You know how amount of false positivity rate that you would want to tolerate. So you give it enough size. But in case you would want to do that, you know how to do it. What you do? You first create a new Bloom filter with a large size. You go to your actual database, iterate through all the keys that you ingested. You ingest it in this Bloom filter, because now your hash function has totally changed, and then you start serving it. Right? So this is how you would take care when you'd want to scale a Bloom filter. But it's always better to start with something big enough. And to be honest, 1 KB is good enough for most use cases out there, unless you operate at massive scale. So which is where that formula comes in, that hey, you know the maximum keys that you would put in, you know the false positivity rate, which would help you derive the maximum size of the Bloom filter that you would want to start with. Right? Okay. But do we need to build your Bloom filter every time? Not really. Redis, one of the most amazing databases out there, they offer you Bloom filters. They offer you Bloom filter as a native data structure. You just create a Bloom filter on Redis and get things done. Use it as a black box. You don't have to worry about much. Right? Redis can also take care of scaling of Bloom filter if required. Typically, you should pass in the maximum size that you are comfortable with. But no, actually, sorry, my bad. Redis does not give you that. I thought it was other database, my bad. Redis does not give you that. So when you create a Bloom filter on Redis, you have to specify the size of it. So the default is, I think, 1 KB or 10 KB. But when you are creating a Bloom filter, you can specify the size of it and false positive and whatnot. And then you can start putting data in, right? But when you would want to enlarge a Bloom filter, it's your responsibility to re-ingest the keys. So once you create a Bloom filter, the size is fixed. You cannot change it, right? So which means you need to be very aware of how big your Bloom filter is going to be, right? So that's a challenge that comes in. That is where that formula that I talk about, the maximum number of keys that you would ingest, the false positivity rate that you would want to tolerate determines the length of the Bloom filter that you should have, right? Okay. Now, practical applications of Bloom filter. Use it whenever you insert but not remove the data and you want to get very fast reads over there, right? You need a know with 100% certainty. Typically, recommendation engines are a great place for Bloom filters, right? When you want with 100% certainty that, hey, something does not exist, and having some false positivity rate is okay. Because if you cannot tolerate false positivity, that hey, it's okay for you for that Bloom filter to say yes to something, even though that does not exist. If this is not okay for you, then Bloom filter is not for you. So you should be okay with some false positivity. That's only when you can adopt a Bloom filter, right? This is a limitation. But at scale, for example, for Medium recommendation, let's say Medium wants to recommend an article for you, they use Bloom filters for that. So for every article that you read on Medium, they put it in a Bloom filter that, hey, Arpit read this article. And then they just check that Bloom filter, that, hey, does this entry exist or not? But they have to make it space efficient because millions of users are reading millions of articles or thousands of articles. For them, they have to keep those things very efficient in checking and recommending, right? They cannot use a set for that. It would become heuristically slow. You don't want that to happen. Right. Other thing is web crawler. Let's say you crawled a particular way. Why do you want to crawl that again? Which is where you would use Bloom filter in case of web crawlers to mark that, hey, this is a URL that I already visited. I don't want to visit it again. Right. Very space efficient way to check for for non-existence of a certain thing. Then feed generation. You want to add to the feed of a user a post that the user has definitely not seen. Feed generation. Bloom filters. Tinder feed. I want to swipe, like I should not get a person who I have swiped before in my Tinder feed. Bloom filters. So wherever you want with 100% certainty that something doesn't exist, you go for Bloom filter. And in Tinder, it's okay that if a certain person was said, hey, Arpit swiped it, but in reality, Arpit did not, which is fine. If in a crowd of, let's say, 100,000 folks, if I miss on 10 or 100, it's fine, right? Because it's okay to miss out on something, but performance is really important, right? So yeah, this is the idea of Bloom filter. This is how Bloom filter works. This is where you can use Bloom filter and use it with Redis. At least use it with Redis. Redis offers you native Bloom filter features. So as part of exercise, what I want all of you to do is you set up Redis locally, first of all. Second, read the Redis's documentation on Bloom filter. Third, write a small code, simple Redis CLI to use that Bloom filter and see what happens. See how you insert the data, see how you retrieve the data, and try to mimic something, try to see that false positivity rate in that, right? Write a script, write random data into that Bloom filter, but play around with it, right? And then just try to get one false positive result, which means that it should say that this exists, but you know that that doesn't exist. So have a list of keys that you're randomly ingesting and just keeping track of what you have ingested, and then query it and see if it says yes to something that does not actually, that you have definitely not ingested. That would be fun to get a false positivity rate in that. Try to do that. You will have quite a bit of fun while doing it. Right? And I have a huge repository. I did a very detailed deep dive on Bloom filters few months back. So I want you to check out this repository, github.com/arpitbbhayani/abloom. So it's Arpit's Bloom, that's why a Bloom. It has the code for Bloom filter in Golang in case you are interested. It has multiple variants of Bloom filter, multiple benchmarks of Bloom filter, how false positivity rate changes as you insert more keys, and how to, like, to find a ton of statistics around it. You go through that repository, go through that source code to build even deeper understanding of Bloom filter. Take your time. There is no hurry. Take your time, go through that repository, understand that code, understand how false positivity rate impacts Bloom filter, the correctness of the system and whatnot. You'll have quite a bit of fun while exploring that. And this is what I wanted to cover about Bloom filters. I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.